Today we are going to be learning more about isotopes and how we can calculate the RAM or the relative atomic masses of elements from their masses and their abundances. To begin with isotopes, you have to understand what isotopes are. What are isotopes? If they ask you this question, drop the answer at the comment section right now. Isotopes are atoms of the same element having the same atomic number or proton number, but different mass numbers due to a difference in the number of neutrons. They don't all have the same number of neutrons. That is why they are existing with the same atomic number but different mass numbers. All isotopes share certain features, certain characteristics, some which are the same and some which are different. For example, physical properties. Let's talk about the physical properties of isotopes. All isotopes have different physical properties. The physical properties of isotopes are not all the same. We are going to be listing some of the examples of isotopes, and you see that their physical properties will not be the same. Their masses are not always the same. Their boiling points and their melting points will not always be the same. That is why they have different physical properties. Physical properties are those features that we can perceive with our senses. Now, talking about chemical properties. What about the chemical properties of isotopes? Drop your answer in the comment section right now. All isotopes have the same chemical properties. The chemical properties are the same because in chemical reaction does not depend on the mass or the size. It depends on the combination. They all have the same reactivity. That is why they're having the same chemical properties. Now, talking about the representation of isotopes. Isotopes are represented with a symbol. Let me use X as a symbol. And up here, you have the mass number of that isotope and you have the proton number down here. That is how all isotopes are represented. Let's talk about the various examples of isotopes so that we can further explain this concept. Hydrogen is the first example. Hydrogen exists as three different isotopes. We have hydrogen 1, hydrogen 2, and 3. This is hydrogen 1, the same atomic number but different mass numbers. Hydrogen 1 here, and this is hydrogen 2, atomic number but different mass number 2. Hydrogen 3, the same atomic number, different mass number, which is 3. All these three isotopes of hydrogen have their various names. The first one is known as protium. The first isotope of hydrogen is known as protium. And the second one is known as deuterium. The third one is known as tritium. These are the three isotopes of hydrogen. When looking at all these isotopes, you notice that their neutrons are not the same. Their neutron number are not the same. How do you know their neutron number are not the same? For example, let's calculate the neutron number of this first isotope. Neutron number is calculated as the mass of that isotope minus the proton number. The mass minus the proton number gives you the neutron number. So this is the mass up here and the proton number, which is 1 minus 1. You can see that this one has 0 neutron. The second isotope's mass minus the proton number, which is 2 minus 1, has a neutron number of 1. And you can see this other one, 3 minus 1. You can see that the first one having 0 neutrons, second one having 1 neutrons, and the third one having 2 neutrons. They are not all the same. That is the reason why they all have different masses. Because of the number of neutrons, they are different. Let's talk about the second examples of isotopes, which is number 2. The second example is chlorine. Chlorine exists with two isotopes, chlorine 35 and chlorine 37. Chlorine with a mass number of 35. Chlorine, the proton number of chlorine is 17, right? And you have chlorine with a mass number of 37 and the atomic number or the proton number remain the same, 17. These are two isotopes of chlorine. Carbon also exists as isotopes. We have three isotopes of carbon. Carbon 12, 18, and 14. So carbon 12, the mass number is 12 at that moment. And the mass number of the first one is 12. And the proton number is 6. The second one is 13. The mass number is 13. The proton number is 6. And the third one, carbon, is 14. Why the proton number is 6? Let's come to this chlorine and calculate their neutron number. How do you calculate neutron number? The mass number minus the proton number, which is 35 minus 17. What is 35 minus 17? This first one is having 18 neutrons. Chlorine 35 is having 18 neutrons. Let's talk about chlorine 37. 37 minus 17. Chlorine 37 is having 19 neutrons. So these are the differences. You can see that the neutron numbers are not the same. That is what is contributing to isotopes having the same proton number but different masses because of the difference in the number of neutrons. Let's talk about the carbon here. Carbon 12. Let's calculate the neutron number of carbon 12, which is 12 minus 6, which is 6. So this first isotope is having 6 neutrons. Talking about the second one, 18 minus 6, which is 7 neutrons. And talking about this other one, 14 minus 6, which is 8 neutrons. You can see that their neutron number are not also the same. The next isotope we are talking about is oxygen. Oxygen also exists with 3 isotopes. You have oxygen 16, 17, and 18 with the same proton number. Oxygen 16 and the proton number is 8. You can also have oxygen 17, the proton number still remains 8, and oxygen 18. The proton number still remains 8. So if you want to calculate the neutron number, you will notice that the neutron number are not also the same. That is what is contributing to the difference in their masses. Talking about the uses of isotopes, these isotopes are also important in various aspects of life. Isotopes are important in medicine to treat diseases such as cancers. Isotopes are also important in agriculture to kill pests. Yes, we can use some isotopes as pesticides used in killing pests. It is also used in industries. Isotopes are also used in industries to detect pipe leakages. Those are the use of isotopes. These are the three most common importance of isotopes, even though we still have so many other importance, but these ones are the most common ones we can list now. Okay, talking about relative atomic mass. What is relative atomic mass? RAM. Relative atomic mass is the average, average mass of the naturally occurring isotopes of that element. Relative is a comparison. Relative to 112, the mass of carbon-12 isotopes, the average mass of the naturally occurring isotopes of that element, relative to 112, the mass of carbon-12 isotopes. That is what we call relative atomic mass of elements. As you can see, all elements that exist in nature all have a relative atomic mass. For example, chlorine has a RAM or relative atomic mass of 35.5. You can talk of oxygen. Oxygen has a RAM of 16. Carbon has a RAM of 12. You can talk of sodium have a RAM of 23 and so on. We have so many elements with their different RAMs. Those RAMs were being calculated from their isotopes using their relative atomic masses and their abundances. To get the relative atomic masses of elements from their masses and their abundances, you use this formula. RAM is calculated as the sum or summation of the mass and the abundance of those isotopes divided by the total abundance. We can further simplify this as the first mass times the first abundance, all this plus the second mass times the second abundance. Yes, it depends on the number of masses that we have. If we have more than 2 isotopes, we keep on summing their masses till we reach the final end. All over the total abundance, you sum up the abundances. Abundance 1 plus abundance 2. But if abundances are given in percentages, we will always sum up to 100%. So you can always use 100% or 100 where you have total abundances. Take down this question. Copper has 2 isotopes. These are the isotopes of copper, 63, with the abundance of 69.1%. The second isotope of copper, 65, with the abundance of 30.9%. Calculate the relative atomic mass of copper. In this question, we have all the data that is needed for us to solve. We have the mass is the mass of the first isotope and the abundance of the first isotopes. We have the mass of the second isotope and the abundance of the second isotopes. So what are we going to do here? Using this formula, we have mass 1 times abundance 1. All this plus mass 2 times abundance 2 divided by the total abundance. So to solve this, I'm going to input the various data in this formula. The mass 1, the mass of the first isotope is 63 times the abundance of the first isotope, which is 69.1. All this in bracket plus the second mass, the mass of the second isotope, which is 65 times the abundance of the second isotope, which is 30.9. Yes, after doing this, you divide all through by the total abundance. Like I said, the total abundance is over 100%. If you sum these abundances, it will give you 100% or 100. So after doing this, you can calculate in your calculator and get the answer. So I'm going to take 63 times 69.1, 4,353.3, plus, make sure you multiply the other ones as well. You have 65 times 30.9. The answer is going to be 2008.5. Divide all these by 100. Summing the two numbers at the numerator, I'm going to have 636.1.8. Divide all these by 100%. So if you divide all these by 100, I'm going to have 63.6. So our conclusion is that the copper has a RAM of 63.6. You can always use this particular method to get the relative atomic mass of each element you have been given. If you find this video helpful, hit the like button. Subscribe to this channel so that you are not going to miss any of my video which is going to be dropping.